I'm combining 7.1 and 7.2 to talk about exponential growth and exponential decay. Exponential growth is where you start out with a little bit, but then it grows exponentially. So something like this, like you start out really close, but then you grow as the x values get larger. Exponential decay is the opposite. As time goes on, the values get smaller and smaller and smaller. So think about this in a real world situation. Like exponential growth is maybe you deposit some money in a bank account. Over time, the interest grows and the amount gets more and more and more. And the amount of interest you get grows exponentially because you have more money in the bank. Exponential decay, maybe you can think about it as like you take some ibuprofen or some Tylenol or something. You start out with a certain amount, and over time, that amount gets less and less and less and less until it becomes zero. It decays over time. The most basic form of an exponential growth equation or exponential decay is f of x equals b, some number b, to the x power. And you can determine if it's exponential growth or decay just by analyzing the b. If b is greater than 1, this is exponential growth. If b is greater than 0, but less than 1, so some fraction between 0 and 1, it's exponential decay. Something you need to know about exponential growth and decay functions is, over here and over here, it's going to get very, very close to this x-axis, but it's never going to touch it. It'll get less and less and less, and it'll become so close to 0 that we will approximate it as 0, but it will never actually touch this. We call this line that it gets really close but never touches an asymptote. We call it an asymptote. It's vocab you need from this section. So this line, so now that we know the asymptote is this line that it will never touch, we can tell the domain and range. So for example, the domain for this growth one on the left, the domain is all x values because it stretches to the left on the x-axis and to the right on the x-axis. Domain is all the x values, so all real numbers. But the range, it's stuck at y, it's stuck at 0 because it will never touch that line. And because it will never touch that line, it does not include it as well. So it's not y greater than or equal to 0, it's just y greater than 0 because it will never touch the line. And this domain and range is true for each of these. Now, just like we're used to seeing with the other ones, we can change it by these factors. We can have f of x equals a times b to the x minus h plus k. The a factor out front, it's going to stretch it out or shrink it down, and a negative sign out front is going to flip it. This a factor is also very important because the a factor is going to be the initial amount that you put in. So if you have an initial amount, like an initial population or initial amount of aspirin or ibuprofen you take, that's going to be something that we write for the a factor. It's going to be the initial amount. The b value is not something that changes the equation, but it's just the rate or the factor at which the line is changing, or the percent. So if b is greater than 1, it's growth because it's growing by a rate faster than 1. If it's between 0 and 1, it's decay because it's actually shrinking by that amount, by a decimal point. Of course, up top, the x minus h, that's going to affect whether it moves left or right. And it's going to be opposite, just like we're used to seeing. And the k will move it up and down. But it's also important because the k value changes the asymptote. Now, without a k value, the asymptote is always y is greater than or y is less than 0. The asymptote is always this line. But if the k value is plus 2, the asymptote is now plus 2. It's up here. If it's minus 2, the asymptote is now down here. So it's very important that you know that the k value, I'm running out of space to write this, but the k value it changes the asymptote. So let's take a look at an equation I just made up. So negative 2 to the x minus 2 plus 3. And if you saw this written down, it would look like this. Just so you know, it's negative 2 to the x minus 2 plus 3. And the way we have to enter that into our calculator is like this. The negative sign goes out front. The 2 to the x minus 2, we have to do some tricky stuff with the parentheses there to make sure it knows that we're taking the 2 to that power. And the plus 3. So in this situation, this negative sign is like the a. So the a is like a negative 1. This is the b. The rate is 2. That's greater than 1, so we expect this to be an exponential growth factor. Because the b is 2, it's greater than 1. This is growth. This x minus 2 means we're going to shift this, all of this to the right 2. And the plus 3 means we're going to bring it up 3. And the new asymptote will be at 3. So let's go ahead and graph it like this. So it's hard to see, but if we zoom in a bit, looks like we got to change the window just a little bit. So let's say negative 5 to 5, and maybe negative 5 to positive 5. So what it looks like is this. This negative out front, it flipped it around. It's still an exponential growth function because as the x values get larger, it's still increasing. Decay would mean that it's coming in and like smoothing out or getting smaller and smaller. But this one's actually still growing in the negative direction, so it's still growth. The 2 is just the factor at which this graph is growing, is a factor of 2, or it's growing by 200%. The x minus 2 means it shifted to the right 2. I know it doesn't look like that, but if you put in the original one, it would be to the left 2. And plus 3 means it's moved up 3. And the new asymptote, you can see it here, is actually 3. So if we were going to say the domain and range for this, we would say the domain is all real numbers, because it's all the x values. And the range, gotta take another look. The range, the asymptote is at plus 3. We know that from this equation. The range is all the values less than that. So the range is y is less than 3. There's one more equation we have to talk about, and it's how to calculate interest on a bank account, like if you actually get money, or more importantly probably is how to calculate how much interest you'll be paying on a credit card. So the amount you're going to pay is A, and that's equal to the principal, how much you spend or put into a bank account. We'll do the credit card example. So that's the principal. That's what you start off by spending. Then 1 plus r over n. R is the interest rate as a decimal. Interest rate. N is the number of times you have to pay. So number of times you're supposed to pay. So in a year, of course, this would be 12. That's how credit cards work. You have to pay 12 times per year. The N is that same number, and T is the amount of years. All right, let's say you want to figure out how much you're going to have to pay. If you put $2,000 on a credit card and you don't pay any of it back for a whole year, you're going to do 1 plus R is the interest rate. Credit cards are around 20% interest, so let's say 20%, 0.20. The number of times you got to pay, there's 12 times you got to pay that per year. And to the 12 times 1, that's NT. I don't know why I'd erase that. So calculating this out, you're going to do this stuff in parentheses first, take it to that power, multiply it times 2,000, and you're going to end up paying around $2,438.78, even though the item you purchased was only $2,000.